Hi everyone, in this video we're going to look at measuring correlation. So in the last video we looked at analyzing paired data by plotting it in scatter plots and looking for relationships between the two variables. So we saw this simple example with the number of hours of sunshine on different days and the amount of ice cream sold on those same days. And when we created the scatter plot, we saw this sort of up and to the right pattern where the dots are following roughly a line going up and to the right. This is a positive correlation or a positive association, meaning that days with more sunshine also have more ice cream sold and vice versa. So what we're looking at here is how do we measure that relationship? And we measure it with what's called the correlation coefficient, which is denoted with a lowercase r. And this r value is a number somewhere between -1 and 1. No correlation would be right in the middle, so that is 0. A no correlation graph would be just kind of random dots spread all over the place. There's no linear pattern within the dots. And then a perfect correlation can be either positive or negative. So 1 would indicate perfect positive correlation, -1 indicates perfect negative correlation. So in either of those cases, we're seeing our data values exactly fall along a line. So just visually speaking, looking at our scatter plot from the sunshine and ice cream sales, these dots do show a pretty clear trend up and to the right, but there's a little bit of variation. If I drew a line in between them, we see some of the dots would be a little off of the line. So this is not perfect positive correlation, but it's likely going to be something close to a +1, maybe like a 0.9 or something like that. So you can get values anywhere between -1 and 1, but the closer to 0 the values are, the less linear correlation, the less association there are between those variables, and the closer to 1 or -1, the stronger that relationship is. Now, I did want to mention here, there is a formula for calculating R, an algebraic formula. We're not going to get into this. This is quite tedious to calculate by hand, even for fairly small data sets. So we're just going to use technology to do this, but I did want to mention this is essentially finding kind of the variation from the mean of the x and y paired values kind of together and then averaging them. That's sort of how you might think about the r value. But I'm not going to address this calculation directly, but we will look at an example. So in Excel, the r value is calculated using this function CORREL, C-O-R-R-E-L. I'll pull up this ice cream example. So I've got my data in Excel in these two columns. I'm going to find just an empty cell somewhere and start typing equals, C-O-R-R-E-L, CORREL, parentheses, and then I'll highlight my x values in that first column, comma, and then the y values. It actually doesn't matter which order you do this in. You can switch the x and y values and the correlation coefficient will come out the same. If you do switch the x and y values, that would reverse your scatter plot, and so it can change what you're thinking about as sort of your x or your y or your independent and dependent variables. But for the correlation, it doesn't make a difference. When I press enter, this is giving me 0.965006898 for this data set. So as expected, this is an R value that's quite close to 1, just a little bit below 1. So we don't have perfect positive correlation, but it is very strong positive correlation. We can look at this image from Wikipedia, especially along the top row here. So they're showing us some examples of what data values might look like with different correlation coefficients. So an R value of 1 on the left-hand side here is a bunch of dots that are perfectly along a line. And the slope of the line is sort of how steep up or down it is. The slope doesn't affect the correlation coefficient except for the sign. So a positive correlation with that perfect relationship would be a correlation of 1. A negative sloping correlation will be a correlation coefficient of -1. You can see it's a little bit hidden there. And then in comparison, a 0.8 R value, we see a cluster of points here that are generally forming that upward trend, so up and to the right, but we see variation among those. So it's more like a clump of dots that's spread out along a positively sloping line. And similarly for negative 0.8, just with a negative slope there. 0.4 R value is going to be a little bit more nebulous, a little bit more of just a cloud of points, but we can sort of see in these points that there's an up and to the right or down and to the left trend within them, and similarly for the negative version. And right in the middle, they have a zero correlation example, which is just kind of a cloud of points with no pattern. Now, this Wikipedia image also shows along the bottom row a bunch of different kind of weird shapes of clouds of points that all actually have zero correlation. So the one on the far right here, we've got 4 distinct clouds of points. There's no particular relationship among the whole group, but seeing something like this in data would probably indicate that you have like 4 distinct subgroups in the data. Or the first example on the left here, this cloud of points is forming sort of a wave going up and down and up and down. So there's certainly something going on in those data points where there is a relationship. It's just not a linear relationship. So the key here is that the correlation coefficient is measuring a linear relationship, not necessarily telling you anything else about the data. So with this sunshine and ice cream sales example, we could just kind of see from the graph that this has a high positive correlation. But for something like this second example that we looked at in the last video, this is the enrollment in different schools and child care centers in Colorado with their immunization or vaccination rates. So the scatter plot shows some very interesting patterns here. We have kind of a scoop of values forming, I don't know, a parabola shape facing to the right, maybe. This is a very large data set, so we see a lot of values here. It's a little bit hard to actually see any relationships in this data, but there is kind of an interesting pattern that higher enrollment schools seem to have either high vaccination rates or low vaccination rates. There's kind of a split there. But if we consider all of these paired values as a whole, we might ask, is there a general trend up and to the right or down and to the left? Is there a positive association or a negative association? There's not a very clear association in the visually in the graph. In fact, it looks kind of symmetric from the top and the bottom. But I can check the correlation coefficient just the same way that I did in the first one, even though this one has a lot more data points. So in an empty cell, I'm going to do equals CORREL with my parentheses. Because this is a really large data set, rather than highlighting the individual values for my x's and y's, I'm just going to highlight the entire column A, comma, and then the entire column B. The CORREL function will just ignore the text labels on these columns. But you do need to make sure that there's the same number of values in each row or each column. So we're getting negative 0.15012. On our number line, that would put us right about here. So we're getting pretty close to no correlation here. Though this is a very large data set, which large data sets tend to have lower correlation coefficients just because there can be so much noise in the data. But there does seem to be maybe a slight negative relationship here. That would imply that larger schools have lower vaccination rates and smaller schools have higher vaccination rates on average, but this is not a strong relationship. There's not a clear pattern in this data. But this could be something that we want to investigate. Certainly there's some other interesting patterns we see visually in this data as well. That is it for this video. Thank you for watching.